Hello, hello. It is lecture 20. Lecture 20. Or if your video is flipped, it's lecture 20. Lecture 20. Yes, lecture 20. I'm excited. Lecture 20. We are now moving into that detection of planets thing. Remember that in the previous lecture, we talked about how first we have to understand how dense the solar system is and all the different things that are involved with it, how the formation was created and the motion thereof, right? And here we use the Doppler method, which is a form of one of the tools that we can do when we're figuring out whether or not a planet is moving in a solar system. We can't see the detected. We can't see directly that image, that particular planet, but we can detect their motion going back and forth, right? So that's super cool. Now, how about this other thing? There are two other main ways that we discover planets outside our solar system, right? So we work out those two ways. Way number one was the Doppler method, right? And that's based on a spectroscopic technique. I should probably use those words. This is kind of a word that is often said, but maybe, just to be really clear about this, we talked about the spectra, right? It's spectral lines, or whether or not you can see things moving back and forth in terms of light and so on. And there's the electromagnetic spectrum. You got the colors of the rainbow: red, orange, yellow, green, blue, violet, purple, indigo, maybe in between, along with the other things like radio waves, all the way up through gamma rays, right? This big electromagnetic spectrum and everything. So we've talked about a bunch of those sorts of things, and both here and you've used it in your lab classes. And now spectroscopy is therefore the study of the light, right? And their different colors and how much they're doing, and what, whether something is, in other words, spectroscopy could be, in a sort of a general sense, the study of objects and their colors, right? Now, spectroscopy is a very important tool, and we use that. But then the other way that we do things, like think about what astronomers do when we're taking pictures of things, right? One thing is a spectroscopy, and that one is almost the most complicated because colors are complicated, right? So if you've done atomic spectra lab already, then you'll see that colors are basically something that might look white or something that might look orange. Actually, there's lots of different colors in it. And so that figuring out colors is a little bit more challenging. Something else that you can use, right, which is actually something different, where you're measuring how bright something is, right, not just necessarily what color they are, that's called photometry. Photometry, okay? And so that's really kind of, in a way, talking about measuring the brightness of object. So photometry is the measuring the brightness of something, whereas spectroscopy might be measuring the color of something. Does that make sense? So in that respect, how do we use photometry to figure out whether or not a star has a planet orbiting it? Well, let's think about it this way, right? And this will be in your reading as well. You may have already read it in the chapter that we discussed previously in the previous lecture 19 about finding planets. But imagine that if I am a star here, and then I have a planet that's orbiting the star, right? Let's say it goes around, that way, like once every year or so, something like that, going around and around, right? Going around. Well, I'm just this way, it makes it easier. I'm going around and around once every time it goes around. If my orbit around that star happens to be exactly in the path of me, another person far away looking at it, what you'll see is that for a brief period of time, that planet will block out the light from that star, right? So it's like a sort of a partial blockage, right? Now, a total blockage we often call as a total eclipse, right? In fact, we have that in our solar system, and we mentioned that earlier in the semester, that we get eclipses when the moon, for example, just happens to be exactly in the path between the sun's light and us on any given spot on the Earth at any given time, right? When you have something small pass over something big in such a way that it doesn't block out all the light, but it blocks out some of the light, that's called a transit, okay? And so I'll make this second part here, we'll call it the transit method. not public transit, which is like when we take the metro or the MTA or a bus or something like that. That's public transit. But this kind of transit is when it's moving in front of your object, right? That's the transit method. And that's a little bit interesting because you have to measure something called a light curve. All right, so what is that? Let's draw that. I'll use the other half of this side of paper. Let's say I draw something like this. Here's a map of how bright something is, a graph of how bright something is, and the passage of time. Okay, so brightness. And remember, brightness can either take the form of flux or luminosity, right? Remember that from previous lecture? Right. And then you can also have, this is time going forward. You know, this could be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, something like that. So a star that does not have a planet that transits in front of it, right, will just have measurements that kind of go across like that, right? Every day it'll look pretty much the same, like that, right? That's the data that you would have if there were no planet. But if there were a planet and that planet is transiting, so that it comes across, right, then every once in a while, if you're watching it, then what will happen is that it will have a dip in how bright it is. So it might, you know, look like that if it worked, but instead, you know, a star might instead look kind of like that, like that, like that. Right? You got these dips coming in, dip, 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 like that. So these are the things that could happen. And what you do with your telescope is that you measure it every day or every hour or something like that over a long period of time, weeks, months, maybe even years. And so it's not a perfectly smooth line because you're not watching it all the time, but you take a picture, you take a picture, take a picture, take a picture, measure the brightness over and over and over again. And then after dozens, hundreds, thousands of such measurements, then you find this thing called a light curve. Okay, so these things here are the light curves because it's measuring how bright the light is, and there's some curves in it, right? The light curve of a planetary system that has a transiting planet has a distinctive dip and coming down and back up. Okay, so I'll label this graph as a light curve, and this is how we use photometry, right, to measure or find planets. Now, this might seem really, really hard too. Remember in the previous lecture, we were talking about objects, right? We're trying to figure out like this. Here's a searchlight and here's a little firefly, right? And the firefly is kind of bright here, but the searchlight is so many millions or even billions of times brighter than this thing that you're not going to see anything, right? Because you can't see that little tiny bug in this huge searchlight kind of in this way. But as it passes by, right, it's going to block some small percentage of the light that's coming through. And if you can watch it long enough, and if your photometry is sensitive enough, then you can actually figure out whether or not planet is going by. Maybe it's not a planet, maybe it's a companion star, or maybe it's some random thing that kind of goes right by it, or some strange phenomenon. Maybe the star itself is kind of doing strange things and it's not steadily in brightness all the time. But all those different ways of measuring the light curve can give you clues, and they have different shapes, right? Like there's one famous kind of pulsating variable star. It's called the Cepheid variable, and it's used to figure out how far away objects are in the universe because it has this very cool thing called the Leavitt law that it follows, named after Henrietta Swan Leavitt. She figured out that the period of time it takes for this thing to pulse is proportional or has a relationship that's mathematically describable with how luminous the star is. So it's really kind of cool to be able to use those kinds of methods. But in photometry, in this case, the light curve, we're talking about looking for transiting planets outside our solar system, okay? And it turns out that this was such a useful and meaningful experiment to try to find these kinds of planets, that NASA, about 15, 20 years ago, agreed to spend hundreds of millions of dollars of your tax dollars at work, the federal government, given to NASA, distributed to universities and colleges and research centers all around the country. And they built a telescope that would go up in space. And that telescope is not the Hubble Space Telescope, but it's a specialized kind of space telescope where it would just look at one part of the sky. And it would look at it and all the little stars around it for years. And it would just keep taking pictures, keep taking pictures every few minutes, every few hours, every few days, and just in the spot over and over again over a whole bunch of years. Now, that one spot in the sky is pretty big, actually. It's about the size of the constellation Cygnus, because sort of in the center of the constellation Cygnus, the Swan. So if you take your open hand, right, and you still put it at arm's length and hold it out facing the sky, the patch of sky is about the size of the palm of your hand, roughly, maybe a little bit smaller. But it's a really big area of sky as far as astronomers go, because in that space, if you have a good enough telescope, you can find millions of stars. Right, so it's a lot to do. And so what happened was, for a bunch of years, this satellite, right, again, spending hundreds of millions of dollars, like I said, of our tax dollars. But remember, our tax dollars were going to, when you spend money like that, it's not just like going to a person, right, and they put it in their pocket and do something silly with it. But it's like the money goes to fund technology. It gives to companies to build parts and equipment, aerospace companies to launch rocket, professors all around the country, for example, to have students work with them on research and teach them and how to build these things and to create the telescopes and then the computer software that helps analyze all this. So it's a really complicated process, but many, many people over the years worked on this thing and launched this spacecraft, and they looked at that part of the sky for several years just to see how many of these kinds of light curves they could find. Okay, so this mission was named the Kepler mission because, well, you've heard of Kepler before, right? Kepler's laws of motion talk about the orbits of things. And so since we were talking about planets, they decided to name this the Kepler mission. So this is the Kepler mission, which is basically a space telescope that went up, and we can read about this, and you can see about this in the videos in the study guide. Hope you're filling out your study guide right now. Yep. So the Kepler mission was basically tasked to look at thousands and thousands of stars over a period of months and years, trying to get the light curves about these objects. And guess what happened? It was probably the most successful spacecraft of this kind ever, because what happened was it found more than 4,000 planets. Okay, now remember, these planets, you still have to confirm. Once you see the light curve, that's great, right? They're most likely planets. We're still not absolutely 100% sure because you haven't actually laid eyes on them or found other ways to do them. So they're called planetary candidates often, right? But they're planets that we're pretty sure that they're there. They've been confirmed in different ways. They haven't been falsified yet. They're trying to see, they're always hoping that you can get some really concrete proof that that thing is a planet, not just some strange effect. But we're looking for thousands of planets. Seriously, right? Remember that transit method that we were talking about, right? Using the Doppler effect of the wobble of objects. That was good, right? They found like hundreds of objects, but these things found thousands of planets. Wow. Not only that, these planets don't have to be so big that they pull the star back and forth that they're orbiting. Right? They can just orbit and the pull can be so small as to be indistinguishable, but the light gets blocked. And so you can measure the light. So this is the transit method of figuring out stuff. And that found thousands of planets, all right, which is super, super cool. And then the best thing we could do, we would love to be able to do this for every planet if we could, actually to take a picture. Wouldn't it be great if we could take a picture of a star? Let's just draw a star here, a picture of a star, and then orbiting the star happens to be a planet. Look, star, planet. That'd be great to see. That'd be very exciting, and we'd love to do that. And that kind of technique, see how we had talked about spectroscopy, which is measuring the color, and then we measure the brightness, right? The third kind of way that's used by astronomers to find planets outside of our solar system is called imaging, direct imaging. All right. Now, this is a two-word expression, but it makes sense. Direct imaging is just taking a picture, right? And taking a look and see what the shape is. Do you see two dots or you just see one? right? That kind of thing. So that's taking a picture. Now, this method of finding planets has been attempted, right, long before the technology was developed in order to, say, do a transit thing or do spectroscopy like that, right? Really, really hard to do that. But it turns out that is really, really hard to do. Why? Even though, like, it's the easiest thing to think about doing, like go point telescope up, see if you see a planet going by, right? Is really, really hard. Why? Two reasons. First of all, stars are really, really far away. Okay, so even if I could take a picture of that, the Alpha Centauri, for example, the nearest star to our solar system, is more than 25 trillion miles away. Now, remember, an astronomical unit is like 100 million miles, 93 million miles, 1.5 times 10 to the 8 kilometers. Nothing huge. Are you kidding me? It's a huge distance. But 25 trillion miles is way bigger than 93 million miles. So if we're looking at this thing, the planet and the star would look like they're literally on top of one another. So it's really hard to see because they're just so close to one another that you can't really pick them out, right? Let's say we were able to pick them out that way. There might be a way to do that, right? And in fact, we do. About 20, 30, 40, 50 years ago, we started developing technology that could really pick out these very close by objects and resolve them. It's called resolution, right? It's a thing that means that you can tell them apart. Direct imaging. You could tell them apart just by taking a picture of them, be able to pull them apart using sophisticated computer technology and optical sciences. You can actually like see something that looks like they're all blurred together, actually be able to nucleate them and figure them out apart, like enhancing the image, which is really cool, right? The second thing that you have to deal with is once again that issue of brightness, right? Remember the little tiny fruit fly, firefly, right, flying in front of that gigantic spotlight. Again, we have the same problem. If I take a picture, if you ever take a picture with your camera, right, you take a picture into the sun or something like that, the person that you're taking a picture of, their face is often very dark, right? Unless your camera is really good and like this little mini flash or something like that. It's because the light of the sun behind them is basically kind of drowning out, and all you see, like the camera is adapted to the brightness behind them, and you can't see the front of them so well. That's the same sort of problem, but it's a factor of not just like sunlight versus shadow, but factors of like millions or billions in how bright difference they are, right? So you have to overcome that difficulty. And how do you do that? It is possible. Yes, again, new technology, right? This is the contemporary work. If you're thinking about how you do it in the past, hundreds of years ago, it's the same old thing, but now we do new things. And the trick that astronomers are trying to do is to look at wavelengths that are invisible to the eye, but are visible to telescope detectors. Okay, so if you use infrared light, you do a little bit better. In fact, you do a lot better. A planet like Jupiter, you may have seen this in your readings or in watching the various videos that are associated with when we went through the March of the Planets and stuff like that and talked about all those cool things. Jupiter actually emits a fair amount of infrared light, not so much visible light, but a fair amount of infrared light. Meanwhile, the sun, which produces like the peak of its thermal radiation in visible light, produces a lot of infrared light too, but not nearly as intensely as visible light. Therefore, if you think about it, you're looking away from that mean peak of the thermal radiation spectrum for the sun. So it's not quite as bright as it normally would be. Meanwhile, you're looking at a planet like Jupiter, which is actually quite bright in the infrared compared to the optical. And so those, the huge difference of, billions, a factor of billions in how bright they are starts narrowing down, right? Maybe into the millions or even into the thousands or something like that, right? Then you can do a pretty good job. Because if you take a picture of something and you take a picture of something, let's say something that gets the star, right, the sun correct brightly in 1 second, but this thing down here needs 1,000 seconds to take a look at. By the time you look at the whole picture for 1,000 seconds, this sucker is way like saturated the picture and you can't even see that little tiny planet anymore, right? But if you can take pictures, not one single picture of 1,000 seconds, but you took 1,000 pictures 1 second each, right? So that this thing was actually smaller or less in a given time, you can kind of subtract that out, and then you can actually add up what's left in order to get that little star. Better yet, why don't you take something in your telescope or in your camera and block off that bright star, right? Block off the majority of its luminosity or its brightness or its flux, whichever unit you're using. Block off most of it, right? Like, so, okay, let's do this because it's a fun example. Here's the sun, but if I block it, now you can see my face a little bit better, right? So we want to block that sucker. We want to take the bright shining star over here, block it with something in your thing, right, in your camera or something like that. And then you can study the outskirts of the light from that star, which is lower in intensity. And then your planet, if it's slightly higher intensity, so you use this combination of information or techniques, right? So you're, I'm going to write down all these words because it's fun, because it's stuff that's worth learning about. Okay, so the direct imaging, right, techniques, I'll just write them down on a separate envelope here. So the direct imaging techniques give you what? I told you, right? First of all, you need to increase your resolution. So you want to improve your resolution in such a way that you can always tell stuff apart, even though if they're otherwise would be really blurry together. And that technique, right, is something that we call adaptive optics. So that's a technique, that's a technology that helps us distinguish things, right? Separate them out. Take lots of many small pictures, for example, that sort of thing, right? The second thing that we want to do is to reduce the contrast, right? We want, because how many millions of times brighter the star is, or the outskirts of the star is compared to the planet, we want to try to minimize that. So contrast, how do you improve the contrast so there's not quite as sharp a difference? Well, as we said, the answer is to use infrared light, right? So, so we use infrared light. See, there is a fascinating sort of reverse effect. The longer the wavelength of light you go to, the lower of the resolution you're capable of having. See, so these two kind of compete with one another. You have better resolution, but then, you'll wind up with increased contrast because your wavelength is shorter. If you have longer wavelength, you have better contrast, so less likely to be one drowning out the other, but then the resolution gets worse. So that's why you've got to use this technique, these adaptive optics techniques and so forth, right, to improve your resolution, even though you have gone to longer wavelengths, which would reduce your resolution otherwise. So that's a resolution and then contrast. And then the third thing we were talking about, right, is blocking out light, or let me get the right color pen in this thing. Third thing, blocking reduction, right? Light reduction, blocking out. You want to block out the brightest parts. And the way to do that is by taking a piece of thing, right, and sticking it into the path of the light coming down through your camera or through your telescope. And that's a technique called coronography. C-O-R-O-N-A-G-R-A-P-H-Y. Coronography. Because a corona, right, is the crown. And like, if you remember, we're talking about the eclipses, the stuff around the outside of a star or a sun, or the sun, for example, in our solar system, is a corona, and it has some light. And if you want to study the corona, you got to block out the center of the stuff. And so a coronagraph, right, is a kind of instrument, like a scientific piece of equipment that will allow you to block out the primary bright part of the center of a star, for example, and then allow you to study the corona, or the outside part of the sun. And then just putting that Y at the end means that it is the method, right? The method of using a coronagraph. So using these three techniques, each one of them, which has very sophisticated technology involved and lots of development. Again, National Science Foundation, NASA, Europeans also, they all spend a lot of money to do this, to develop that technology, which is really useful for like lots of things other than astronomy, but the astronomers needed it first because they're really hard to do. So you fund the astronomers and do all this good research, right? And then what happens is that once it gets good, then it can become more useful for everything else. There's lots of examples of that kind of transfer of technology too. And if you haven't figured it out already, part of the thrust of this lecture, right, is we're using technology to try to solve a problem, to look for planets, right? How many planets are there out there in the solar system? I mean, if you could ask yourself, the question might be, how many planets are there? Or are there planets other than our own in our own solar system? And we're looking for other solar systems, or how many other solar systems are there? So just as in the previous number of lectures and so forth, if hang on a second, I'll be right back. Hang on. Okay, back. Sorry for the brief interruption. Of course, for you, there wasn't any rush time because I paused the recording. But anyway, using these techniques, right? What we're asking, as I say in the middle of the previous sentence, in a previous block, we were asking, why does the sun shine? And then as we moved forward in our understanding of the physics, right, and the astronomical, the scientific details, then there were technology being built, such as the Homestake Mine experiment, right, where in Lead, South Dakota, underground, we're detecting solar neutrinos in a big tank of dry cleaning fluid. Remember that sort of stuff? Right. So you have the same sort of circumstance here. And only this time we know what we need to do. We've got the technology to develop. And once we develop it, we will use it to happen. So the combination of using adaptive optics to increase resolution, infrared light detectors to improve contrast, and coronagraphy in order to block out too much bright light in one direction, you get a combination of ability to take pictures of entire solar systems and see stars that have planets orbiting around them. Then you take pictures over a period of months or years and you see these little dots moving around going, wow, those are planets and they're moving. That is cool. So in the lecture material with the various videos that you'll be watching, you're going to see some examples of some of those detections, some of those planetary discoveries. And there haven't been many because this is really hard. It might even be harder than doing either the spectroscopy, right, with the Doppler method, or the photometry, which is the light curves method. Remember that with the light curves method, thanks to NASA's Kepler mission and all the work that's been happening, they've been able to find thousands of planet candidates, right? With spectroscopy, this is usually ground-based stuff. Using the Doppler method, we're able to find hundreds of additional planets outside our solar system. And as far as the direct imaging technique is concerned down here, using this three-pronged technological improvement, maybe dozens of planets have been found. So it's a lot of different things. But when you see a planet going around, all right, over a period of months or years, you know that's a planet, darn it, because it's going around and around, right, in elliptical orbit or something like that. There is no better technological or observational proof that that is a planet than actually you're seeing it orbiting like a planet. So what is the deal? Today, we know that there are thousands of solar systems other than our own, right? And we know that just as when Galileo 400 plus years ago looked at Jupiter through his telescope and saw 4 little moons going around it and going, wow, there are these little moons that are going around. So that thing is like its own kind of cool solar system, right? So that means Earth isn't unique with the moon going around it and stuff. There are things out there that are more than just us. We're one piece of this grand cosmic puzzle. Now we see that's true for solar systems too. And this is pretty recent discovery, right? This isn't stuff that was done hundreds of years ago or thousands of years ago, or even 100 years ago. The first planet outside our solar system wasn't confirmed to exist until about 1995, right? So within our human lifetimes, within just a generation, a quarter century, or 30 years thereabouts, that's when we've gone from 0 confirmed planets outside our solar system to thousands. Right, this whole area of discovering planets outside our solar system now, it's its own thing. When you find a planet, that's outside our solar system, we call it an exoplanet, right? Exoplanet or extrasolar planet. Most people now just call them exoplanets because there's fewer syllables, right? Exoplanets. And so there are websites that will tell you about the exoplanets that have been discovered. But there are thousands more, maybe even tens or hundreds of thousands of more planets that are just waiting to be discovered because there's a lot of data sitting around that humans just haven't been able to process yet. Because we have to use computers to process, but computers are imperfect, so humans have to check them. And remember, the Kepler mission was looking for years at thousands and thousands and thousands of stars. And we're taking pictures of these kinds of things using photometry and spectroscopy a lot. Another new mission was recently launched just a few years ago. It's called TESS, all right? That's a specifically just like Kepler, but even more amazing. Well, Kepler is pretty amazing, it's hard to know. But the TESS mission is designed to show exoplanets all across the sky. Remember, Kepler focused on one patch of sky. TESS is making a whole sky map. And so you're really able to see exoplanets pretty much everywhere in the sky. And there's a lot of data available and a lot of analysis that needs to be done. So believe it or not, if you want to find planets or if you want to help find planets, you're allowed to. There are these things called exoplanetary searches that can involve citizen scientists. So you, for example. So in the study guide, one thing that I'm going to do is to tell you about one of these things. All right, and it's in the zooniverse.org website. And I'd like you, if you'd like, to do some of the work on that, because maybe you will contribute to the discovery of new exoplanets. It's already happened. Many, many new exoplanets have been found by people just like you, not professional scientists, but human beings who learned how to do something and then contributed through a combination of their hard work and then like planetary scientists or astronomers working with computers and other sophisticated technology to confirm, yes, those are indeed exoplanets and other solar systems. So, do that, okay? I encourage you to try because it would be fun. Bottom line, we now know so much about solar systems that the contemporary theories of our solar system are being informed by all these other solar systems that we know about and that we've seen. It's really quite amazing. And what I'd like you to do, right, is to think about that. In the rest of the course materials for this study guide, right, this is sort of finishing up our discussion of exoplanets here. Let me then take you to the next level, because now this is data, remember? We have now found through these facts, data, now we want to understand laws and make hypotheses about planets outside our solar system, about solar systems that are not our solar system. So contemporary theories of our solar system are now being driven by seeing, look at all the different panoply, different varieties of solar systems out in our galaxy, out beyond us. What does that mean about our solar system? I told you already, right, earlier in the semester about the formation of our solar system with all the stuff coming in the center and so forth. I reviewed that a little bit in the previous lecture, right? Well, what about the exceptions? We've found solar systems that don't have their planets in the same place that ours, not by a long shot, right? We have, for example, solar systems with planets bigger than Jupiter, but they're orbiting closer than Mercury, right? They're going around their planets once every few days, and yet they're gigantic gas planets. Right? We call those things hot Jupiters. Now, like, what are they? We've also found mini Neptunes. We've found super Earths. Those things are really, really important to our understanding of all the various things in our solar system. So what I'm going to do in the next lecture, now that we know that there are many solar systems to think about, let's zero in on our planet just a little bit. All right, we've talked about planets in general and what layers they have and how they work on things. But I think it's important for you to understand what our planet is like, because when we know what the planet Earth might look like to people out there, right, then we might have a better sense of what to look for when we're searching for life out there. Make sense? This is where we're going next, right? All these planets lead to the obvious thing. Solar systems exist. They're commonplace. They're made all over the galaxy, all over the universe. So, are we alone? Are we the only kind of life as we know it? Let's find out. We'll talk more about that in the next lecture, okay? Meanwhile, finish up your study guides, write anything you have any questions you want, let me know. As always, ask your recitation instructor, ask me, ask your lab instructor. Always happy to have those conversations. Okay, thank you so much. We'll see you at the next lecture. Bye.